So we're going to talk about lattice enthalpy today, and as ever, please like and subscribe and share, because I want everybody to enjoy, hopefully, and get some learning from these videos and my fun shorts that I make. Okay, we've got enthalpy change of solution and hydration. I'm going to talk about that, and then in the next video we are going to talk about how the enthalpy change of solution and the lattice enthalpy are affected by certain factors. But for now, we're going to explain to you how to calculate these different things. To do that, you need to know the definitions, and here is your definition of the enthalpy change of solution. Now, you can remember the enthalpy change of solution because you know the equation for enthalpy change of solution. So delta sol H for potassium chloride. So we're going to talk about potassium chloride, and you can see potassium chloride is here, and it's being added to water and making it aqueous here. And we've got an exothermic reaction right here because it's minus. Now, it can be exothermic or endothermic. Now, let's go how you can get the definition from the equation. So 1 mole of a solute. Well, here's our 1 mole of a solute, and we're dissolving it. And we've dissolved it. Okay, so actually knowing the equation can give you the definition, but you do need to know the definition. Everything in green you need to know. Now, let's look at the next thing, which is hydrated ions. You may have to draw hydrated ions, okay? And they're very similar to doing hydrogen bonding, but a little bit different because there's an ion at the center instead. Ionic lattices will dissolve in polar solvents, like water, okay? And the water molecules, okay, surrounding each ion cause the ions to become hydrated. So first of all, that's dependent on a water molecule, and a water molecule has a dipole here, okay, because the oxygen is more electronegative than the hydrogen. And then in here, you have a Cl- and a K+. So it's ionic, K+, Cl-. Cl- is going to become attracted to the positive part of the water, and the K+ is going to be attracted to the negative part of the water. So let's do some fantastic little animations to get that happening. There we go. So we know we've got the plus and the minus. It's dissociated in water, which is what all ionic substances do. They just break apart, and then let's put all the dipoles on, okay? And you can see all of these dipoles, and you see our minuses are attracted to our positive, and that's a picture of a hydrated ion. Let's draw the attractions in. There you go. So your attractions are in. Try and do this yourself on the other one. Try and draw the attractions in, draw the dipoles, okay? Try and keep the video interactive. Okay, so we have got the dipoles, and from the dipoles, we then put in the attractions. Okay, so I always notice as well, I'm a bit like a floating head and arms. Isn't that great? Okay, so basically, that's so you can see all of the writing, by the way. But anyway, so we've got our hydrated, we've got our hydrated. Let's move on to the enthalpy change of hydration. The enthalpy change that accompanies the dissolving of 1 mole of gaseous ions in water. Okay, so that's 1 mole of gaseous ions. Okay, and that's 1 mole of gaseous ions. This is a gaseous ion now hydrated, now turned into a hydrated ion like we've just drawn. Now this is just an exothermic, so it's exothermic only, but let's go through this definition first. 1 mole of gaseous ions, yes, tick. Okay, in water, tick. Okay, it's dissolved, tick. Okay, so that's the kind of thing. Please excuse that. Okay, now if that is the case, we are going to know that that's exothermic, okay, and the exothermic process, the bonds are being made, and that's why it's an exothermic process. So if it's the case, well, let's go back. Let's go back all the way through it and look at this. These are the bonds you're making while you're doing it. So you're making a bond, and when you make a bond, it's an exothermic process. When you break a bond, it's an endothermic process. So you put energy in to break bonds, energy comes out when you make bonds. And these are the bonds we're making when we're hydrating these ions. So let's go back through it again. And so you've got this hydrated, so energy is given out because I'm making a bond between the water and the ion itself. So they're always going to be exothermic, always exothermic. Can't say that enough because bonds are being made. Okay? And that's really, really important. Now, if I then move on to here, and I'd like you to stop the video, and I'd like you to try and recognize what kind of changes these are. So stop the video and try and recognize what these changes are in front of you. First one, lattice enthalpy. Okay, so lattice enthalpy, which we did in the previous video, is 1 mole of an ionic lattice made from its gaseous ions. Okay, it can't be measured directly, so you have to do it with the Born Haber cycle. This one, you've got 1 mole. Again, all definitions are based upon 1 mole, apart from one, which is the enthalpy change of reaction, but all the others are. Okay, so 1 mole of a solid. Oh, it's gone aqueous. Okay, that's got to be the enthalpy change of solution. Okay, and often these ions aren't separated, they're basically just joined up, and it says LiCl aqueous. If we look here, lithium gas going to lithium aqueous. Okay, that's the enthalpy change of hydration, so hydrated ions. And this is the hydrated ions there. Okay, right, so we've done that. Let's quickly go into a Born Haber cycle. So we can do a Born Haber cycle, but this time relating to lattice enthalpy and enthalpy change of hydration and solution. Now, they're only written in 2 ways. We're going to go through both examples. So we've got all our data here, and you notice we've got all of the numbers apart from the lattice enthalpy. So we want to calculate the lattice enthalpy. So in the exam, you're going to be given this. You will not have to draw this, you'll be given this, and sometimes there'll be gaps. So lattice enthalpy always goes on the left, and it's exothermic, therefore the arrow goes down. Okay, in this case, you know that the solution is minus 37, which is exothermic, so that goes down. And then on the right, you've got the hydration enthalpy. The hydration enthalpy, again, is exothermic. Bonds are being made between the water and the ions, and therefore exothermic, and therefore the arrows go down. So on both sides, we've got, in this one, we've got the arrows going down. So we have a nice Born Haber cycle, a nice little diagram like this. What we can do is we can look at the arrows that are going in the same direction. So again, follow the line. And then you say, oh, okay, right. Okay, the hydrations are going into a different direction to the lithiums. Oh, sorry. The hydrations are going in a different direction to the lattice enthalpy and to the solution. So let's add the lattice enthalpy and the solution together. And let's add the hydration enthalpies together. Now, if that's the case, this plus this will be going to that one plus that one. And that is based upon Hess's law of Born Haber cycles. You really should watch the lattice enthalpy video before you do this one. Okay, so let's get this across and let's do the calculation. So that means these two, the orange ones, are equal to these two, the white ones. Okay, the question itself, if this was a question, would be calculate the lattice enthalpy. So calculate the lattice enthalpy. So I've got the lattice enthalpy here, okay? And that lattice enthalpy, then all I have to do is minus the solution away from the other two. So I've minus the solution there, okay? And then I just put the numbers in. So I put the numbers in, and there you go, minus 825 kilojoules per mole. Now that is the simplest one. We're going to go in the next section, just go into something slightly more complicated, but not much more complicated. Remember, you don't have to draw these Born Haber cycles, you just have to fill in the gaps sometimes. So for example, always remember hydration is on the right, and always remember that your lattice enthalpy followed by your solution is on the left. Okay, so that's all you have to remember is what's on the left and what's on the right. So we're on to our second example, which is to do with magnesium chloride and the enthalpy change of solution. We have got our changes that we need here. Lattice enthalpy, solution, hydration, hydration. Right, well, that means basically that I haven't given you the equations, so stop the video, make it interactive, and try and write down the equations. Okay, so that's just enough time there for you to have stopped the video. Okay, let's start again. So we've got the gaseous ions going to the ionic solid, 1 mole of the ionic solid and your gaseous ions. And then we've got the solid, 1 mole of your solute being turned into aqueous, and you can write that as MgCl2 aqueous if you want, it doesn't matter. Okay, and then Mg2 plus gaseous going to Mg2 plus aqueous, Cl minus gaseous going to Cl minus aqueous. Now we've been given every change in terms of numbers apart from the delta sol H. The delta sol H we're going to have to work out because it is the question. Okay, so calculate the enthalpy change of solution. Really important here that you realise that MgCl2 though is 2 chloride ions, and therefore I'm going to need to times this number by 2, but we'll come back to that. Now, if this is the case, let's draw our Born Haber cycle. So if you do want to draw Born Haber cycles, you can go onto many websites and find Born Haber cycles or values for all of these things, and you can just look them up on the internet. There's absolutely tons of them. Okay, and just look up the values and then just try drawing them. Now, when you do draw them, you do the lattice enthalpy down the left. So there's your lattice enthalpy, gaseous ions to the solid. Okay, and that's exothermic always. Then you do the hydrations on the right. So if you do your hydrations on the right, I'll do my metal first, and then I do my non-metal. Okay, remember that non-metal is going to be times by 2. Now, they will give you this Born Haber cycle because solution can be negative or positive, can be endothermic or exothermic. So therefore, this number here can be, this arrow can be up or down. You don't know, and so if you're so they would give you this Born Haber cycle before you started. However, in all Born Haber cycles, you add this white one to this white one and this orange one to this orange one, and they equal each other every single time, every single time. Now, if I'm going to do the calculation, I have to do times by 2. Okay, that's because inside magnesium chloride is 2 chloride ions. Okay, so as I said, the 2 white ones are going in the same direction, and the 2 orange ones are going in a different direction. So the 2 orange ones are equal to the 2 white ones. Let's move it to the side. Okay, and then let's do the actual calculation itself. So if we're doing the calculation, we can look at this in a simpler way. So I'm going to label this as A, and I'm going to label this as B. And the labels don't matter. You can make any label you want. This is C and this is D. Remember, the orange ones are added together and the white ones are added together. So therefore, A plus B is equal to C plus D. If that's the case, I want to work out B. So B is going to be equal to C plus D, and we're going to then minus A from it, okay? Now that's a simple way of doing it instead of writing out all of these big titles in your exam, and it's quicker. So I'm just doing that to try and help. Now, if that is the case, we then just substitute the numbers in. So I'm going to do delta sol H, and that's going to be equal to, I've got C, so let's go and find C. That's minus 363 times 2. Don't forget your times by 2 because there's 2 chloride ions. So it's minus 363 times 2, and I've done C. Now I'm going to add it to D. So add it to D, so D is minus 1120. Okay. And then we're going to minus A. So if we minus A, minus, it's a minus, and you get that, okay? So if we do that in step, we are going to get, hopefully, plus 122 kilojoules per mole, okay? And that is our final answer. So that was our final answer for this. So remember, it's as simple as you'll have this already. They might have left some gaps here for you to fill in, but remember the lattice enthalpy is always on the left. Then we go into our solution, and then we have hydration on the right. Hydration is always pointing down because it's exothermic. Okay, solution can be either way. Okay, so the arrow can be going up or arrow can be going down. However, if they're asking you to calculate it, they've got to give you this whole Born Haber cycle so that you know whether it's going up or down. But either way, the calculation is always, in this case, A plus B going to C plus D. It's always, every single time. It's these two added together. Depending on whether that arrow is going down or up, doesn't matter. It's still these two added together. Solution added to the lattice enthalpy equals the hydrations. Okay, so it's always exactly the same. After this, we're going to go over one final example where we talk about a slight complication, but most of it is exactly the same as what you've done here. So in our final question on calcium bromide, we're going to do the enthalpy change of hydration. Okay, and we've got our equations here. Nothing to stop you just trying to calculate the enthalpy change of hydration yourself. Stop. Try and do the enthalpy change of hydration. And the one we're going to try is the bromide. Okay, so you can see the bromide down the bottom there has no value. So you can try that one. Okay, let's put this to the side. Okay, and then we're going to make our Born Haber cycle again. It's a good thing for you to try and do it yourself. So here we have the lattice enthalpy going down the side. Okay, and then we put our numbers in. Okay, and then we have our hydration of the metal, if you can see here. Okay, and then we've got our hydration of the bromide. Okay, we've got our solution, which is exothermic, so that's pointing down, and that gives us this. Now, you've got the two white ones. Okay, let's put the final equation in there. You've got the 2 white ones, and also really important, the 2 orange ones, and then you've also got this 2 times delta hide H. Now that's really important. That's where they're going to try and make you make a mistake. Because calcium bromide, the formula is CaBr2, that means you'll hydrate 2 bromide ions. If you hydrate 2 bromide ions, the number here has to be times by 2, okay? Because basically the definition of delta H hide or delta hide H is when you hydrate 1 mole of ions, and we're hydrating 2 moles of ions. Okay, so that means that when you're doing the final calculation as well, this bit which you calculate, so this bit right here, so this bit that we calculate, the value for it will be 2 times the hydration. So our final value, if we want to find what the enthalpy change of hydration of bromine is, and we will have to divide by 2. Okay, now in there we've put it so it's balanced, but the enthalpy change of hydration, remember, is 1 mole of bromide. Now, as we said, we've got the 2 white ones going in the same direction. We've got the 2 orange ones going in the same direction. So the 2 white ones equal the 2 orange ones, put it to the side, and have our calculation come up. So what we've done here, very simple. I can label this A, B, C, and D. So you can see here that I have labelled A and B, the hide, and the hide of the calcium and the hide of the bromide. So this would be A and B, and I'd label it like that, and then the white ones would be C and D. Okay, and that's an easy way of doing it. If you don't want to write all of this out, you can write all of this out, but if you don't want to, you can label it that. Now, if that's the case, we minus away the hide of the calcium to leave the bromide behind. Now that is only the bromide if we divide by 2. So we've divided by 2 here. Okay, so C plus D minus A, so minus this, okay, is going to equal 2 times, and then I take this whole thing and I divide it by 2, and I've simplified it down here. If you divide it by 2, you get minus 359. Okay, and a quick check for you is all enthalpy change of hydrations are negative, so if you get a positive number, you've put the numbers in wrong. Now, that is the final part of enthalpy change of hydration calculations. There's another video next which tells you how the enthalpy change of hydration is affected by atomic and ionic size and things like that. So please go on to that, and please share, subscribe, let everybody know about these videos. Thank you very much.